Hi Year 12, so this is the written section. So let's have a look at question 1. So you've got a cyclist moving up a slope. The slope is at 19 degrees to the horizontal. And you're told the mass of the cyclist and the bike is 85 kilograms. We had quite a lot of trouble with this first bit, so again we're struggling with resolving our vectors. So it asks you to calculate the component of the weight of the cyclist and the bicycle together parallel to the slope. So you're trying to find the component of the weight that acts along the direction of the slope. So remember, we've got like triangles. We can resolve the vector for the weight into the component that is perpendicular to the slope, so this one, and the component that is parallel to the slope. Now, according to like triangles, if this is 19 degrees, then this will also be 19 degrees. Okay, so here's my little right angle. I've got my hypotenuse, which is the weight. I've got opposite, I've got adjacent. If you are struggling with this, I'm going to sit with you in today's lesson and I will go through this with you again. But always remember, down the slope is sine. Okay, so you've got the mass multiplied by g to get the weight, multiplied by sine 19 gives you 271 newtons. And then the normal reaction force is the component that's at right angles to the slope. So that will be equal to this component of the weight, because obviously we don't have the cyclist moving up off the ground or sinking into the ground, so the component of the weight down must equal the same value in size to the normal reaction force. So in that case we've got W cos theta, and we've got the mass multiplied by gravity to give the weight, multiplied by cos 19 gives us 788 newtons. Now the next bit was a bit trickier to get your head around, but you've got to take it slowly, step by step. It says at the bottom of the slope the cyclist has a speed of 5.5 meters per second. The cyclist at this point stops pedalling and applies the brakes, which provides an additional decelerating force of 250 newtons. Determine the distance taken for the cyclist to stop, assuming air resistance is negligible and there are no other forces. So you've just calculated previously that you had 271 newtons of force as the component of the weight down the slope, and you're now adding an additional braking force of 250 newtons by applying the brakes. Okay, so you're going to find the total force opposing the motion by adding the two together. Okay, because any force that's in the opposite direction to the motion of the bike will cause deceleration. So we add these two together and we get 521 newtons. This is the force causing the deceleration. It's the resultant force on the cyclist at this point. We divide that by the mass to find the acceleration. Okay, so total force divided by the mass gives us our deceleration of 6.1 meters per second squared. Okay, that's not the finished answer though. That only gives us the acceleration. We were asked to find the distance taken for the cyclist to stop. Okay, so we now know that we've got a constant acceleration, so we can use suvat. Okay, so let's look at what we have. We're trying to find S. We're told in the question that at the point where he applies the brakes, he has 5.5 meters per second. We want to know the distance to come to rest, so the final velocity must be 0, and we've just calculated the deceleration. We're going to use v squared is u squared plus 2as. We're going to rearrange to find S. Final speed minus initial speed is going to give us minus 5.5 squared because v is 0. And then 2a is just 2 lots of the 6.1. Plug it all into your calculator and you will get 2.47 meters. Okay, in the next part you've got a ball being released near the surface of the moon at time t is 0. The point of release is on a straight line between the centre of the Earth and centre of the moon. So there's like an invisible line connecting these two. Helps if you sketch it out sometimes. If it's released near the surface of the moon, the gravitational field of the moon will dominate. It's going to fall towards the moon. Okay. The graph below shows the variation with time t of the displacement s of the ball from the point of release. Okay, so we can see that initially we considered its position wherever it started to be 0. We then see that the s value becomes more negative, and intuitively we know it's falling towards the moon. So that tells us that becoming more negative is considered to be towards the moon. Okay, so positive must be being taken as up in this case, which means it would be moving away from the moon, and negative must mean towards the moon, because that's where the ball is going. So you have to reference that. You have to not just say, oh, the negative value indicates the direction. That's the general form of what the negative sign means. You're asking in this particular question what the significance of that is. So you have to apply it to the question and say what direction that has been stated to be. Okay, so positive is away. Any negative values means towards the moon. In part B, you are asked to to estimate the velocity of the ball at time is 0.8 seconds. So you've got a displacement against time graph, so the gradient of the graph is velocity. That's the first thing to be aware of. But we have a changing velocity, so therefore we have to take the time that we're interested in, which is 0.8 seconds, and we have to draw a tangent to the graph at that point, and we calculate the gradient of the tangent to find the velocity at that instantaneous point. So I drew my tangent on, I chose 2 easy points to measure, and then I found my gradient by doing change in y over change in x. Okay, so choose 2 points on your tangent, plug them in, and when you do that you should get around 1.3, 1.4, but it's obviously a negative value in meters per second. Have a go at that now if you didn't get that right when you did the test, and see if you can get a close answer to mine, so that you can be confident that you're good at drawing tangents. Okay, and the next bit of the question, it asks you to calculate a value for the acceleration of freefall close to the surface of the moon. So everything we've done so far, if I look back, has been looking at a ball falling towards the moon, and we've managed to find a value of the velocity of the ball at a specific time. Okay, now I can find the acceleration by doing the change in velocity over the time taken. So hopefully you can see that initially the gradient of the graph is 0, so we start from rest. We then worked out the velocity down here, so we can find the change in velocity over this time. Okay, we've got a change of 1.4 because I start from rest over the 0.8, and I get an acceleration value of close to 1.75 meters per second squared. Okay. In part D, you are asked to calculate the speed of an identical ball, so same ball, but this time it's falling 3 meters from rest, close to the surface of the Earth. Okay, so now acceleration due to gravity is not going to be what it was on the moon. You're going to get a different experience. You're going to get 9.81 meters per second squared. Okay, so we can use SUVAT again because we know it falls from rest, so u is 0. We want to find v because we want the speed at the point where it's fallen 3 meters, and we know that close to Earth g is 9.81. You're expected to remember that number. Okay, and so we can rearrange this equation. We get rid of u, so we get v squared is 2as. If we square root that, we will get v. 2 is just a constant. A is acceleration due to gravity, is 9.81. And s, we're told, is 3 meters. When you plug that in, you'll get 7.7 meters per second. Okay. Now the next bit, sorry it's over 2 pages, asks you to sketch on the graph the variation with time t of the displacement s from the point of release of the ball, where the ball is dropped close to the surface of the Earth. For this sketch, take the direction towards the Earth as being negative. Now, this could actually have helped you out with the previous question where you're asked about the significance, because they're basically telling you to change the significance. So originally, falling towards the earth would mean moving up on this graph, but obviously you don't have space to do that, so they say, okay, this time you can just say it's negative in value. Okay, so we just calculated that it will have a speed of 7.7 meters per second once it has fallen 3 meters. Okay, we know it was released from rest, so we can actually find the time that it would have been at when it reached 3 meters just by using another Suvat equation. So you've got time as change in velocity divided by acceleration. Okay, we know it was initially at rest. We know that it reached 7.7 meters per second when we were at 3 meters, and acceleration was constant, it was due to gravity. So that must mean that we reached the 3 meter point at 0.78 seconds. Okay, that allows us to plot on our graph. Okay, so at 0.78, I think I just said, 0.78 seconds, which is about here, I had reached the 3 meter mark. Now again, remember we're taking negative for this to be able to plot it. So I know that that must be a point on my graph. I know I released the ball from rest, and I know it accelerates, so I know the velocity is going to increase. Okay, so the gradient is going to increase. So we're going to start horizontally again, and we're going to pass it through that point. Sorry, it's not a great drawing, I'm trying to rush this, but so long as you've got the same general shape but a greater velocity at any point, because of the fact that it's towards the earth rather than the moon, and you have passed through this correct point of 0.78 and 3, you will get the marks. Okay, in question 3, you're asked to state the law of conservation of linear momentum. Lots of you got 1 marks rather than 2. You said that the total momentum before a collision is equal to the total momentum after a collision, but you didn't give the thing that you needed to say, which is that you needed to say it was inside of a closed system. So another way of phrasing that would be provided there are no external forces. Okay, now what that means is you're only considering the objects that you're looking at the momentum of and the interaction that they have between themselves. You are not considering anything else. That's what a closed system is. Okay, so you have to have referenced that, or otherwise momentum will not be conserved. Okay, this question I think you all really struggled with. Let's have a little look. A toy car crashes into a wall and rebounds at right angles to the wall as shown in the plan view. Okay, so we've got U going in and we've got V coming out. Okay, the graph shows the variation with time of the force acting on the car during the collision. Okay, so you've got this graph. Now I'm just going to skip over the graph for a second and show this bit. The kinetic energy of the car is unchanged. Okay, so that means the kinetic energy that the car has here must equal the kinetic energy that the car has here, which means that their velocity values before and after the crash must be the same because kinetic energy is unchanged. That's really important. Okay, you've got your graph of force against time, and it asks you to determine the initial momentum of the car. So we know that it's a force time graph. So the area under the graph is going to give the impulse, it's going to give the change in momentum, because force multiplied by time is equal to change in momentum. But we can see, because the kinetic energy of the car is unchanged, that V is equal to U in value. It's just opposite in direction. So I can replace mv with minus mu. Same value of momentum, just in the opposite direction. Okay, so this is final momentum minus the initial momentum, actually works out to be minus 2 mu. Now initial momentum is mu. So if I do ft divided by minus 2, or 2 just because I'm trying to get the value, the absolute value, it doesn't matter really about the minus sign, I will get mu. Okay, so you can hopefully see that force times time is the area under the graph, and if I half that, I will get the initial momentum. Okay, so sorry, just trying to zoom out so we can see as much as possible. If I take this 24 value, okay, and I track along, and I were to multiply it by 0.16, I would have to half that. But hopefully you can see the area under the graph is actually half of that. So if your total area is the area swept under the triangle, then half of that area is this section. This is ft over 2, okay? This is the area under the graph divided by 2. So I'm going to take half multiplied by 0.08 multiplied by 24 gives me half of the area under the graph, which is why I get this sum. And when I do that, I will get the initial momentum of the car, and that works out to be 0.96 kilogram meters per second. Okay. Now, we just worked the initial momentum out and got this value, and we're told in the question the mass. So I can use these two values to find the initial velocity. Just do mu divided by m. And when I do that, I get 1.2 meters per second. Okay, so that tells me that initially we had a speed of 1.2 meters per second. It then asks you to find the average acceleration of the car before it rebounds. Okay, so I know that acceleration is change in velocity over time. At the instant where it has 0 meters per second of velocity, it's the point where it's halfway through its collision. It's slowed down to 0 and it's about to speed back up. Okay, so it will coincide with this point in time. Okay, therefore I can say that it went from 1.2 meters per second to 0, sorry, wrong way around. It went final speed 0 from 1.2 in the time of 0.08. I take that from the graph here. Okay, that will allow me to find the average acceleration before it has rebounded. Okay, this one was not done too well, so let's talk about this quite slowly. You're asked to draw a graph to show how the momentum of the car varies during the impact. You don't need to give any values, but you do need the correct shape. So I've re-sketched the graph that you are given, okay, which was force against time. Now force was always positive. It was increasing and then it was decreasing, but it was always positive in value. Okay, during the first section, the force was increasing. Force is proportional to acceleration, so therefore the acceleration was increasing. Okay, at the second half, the acceleration decreased again because the force was decreasing. Now, momentum is mass multiplied by velocity. Okay, if I plot momentum against time, the gradient of this graph is mv y over t x. But v over t, velocity over time, is acceleration. Okay, so the gradient of the graph is actually equal to ma. It's equal to the resultant force at that point. Now, the mass of the car is constant. Okay, so we can ignore this and say, well, then the gradient of the graph that I have to plot must be directly proportional to the acceleration that the car was experiencing at any point. Now, you can see that the acceleration was increasing up until the halfway point. And so the gradient must be increasing in value, okay? It must be getting steeper. We know that we had 0 momentum at the point they were halfway through the collision before they bounced back the way they came, okay? We know that at the start and end, they must have had equal values of momentum, but just in opposite directions. So this height equals this height here. And we know that the gradient here has to increase. We have to get steeper in value because the acceleration is increasing. But from the halfway point, the acceleration decreases, so the gradient has to get shallower, okay, has to get smaller in value. And that's why we get this shape.